and this is my first time in Brazil, and I'm really enjoying it, so thanks very much. So I'm going to talk about, the stochastic resetting, which is a subject that we have been working with various collaborators whom I acknowledge at the end, and for the last few years. And it's a very general sort of dynamics that induces a non-equilibrium steady state. But today I'll just focus on one particular very, very simple, embarrassingly simple model, and just to illustrate the main phenomenon. And so let me start first with the motivation, how we came across this problem. So, so the motivation actually comes from the search problems. So search problems are ubiquitous in nature. So you have searched for Holy Grail in Dan Brown's book, Da Vinci Code, to Higgs boson, to data search in Google, and then animal searching for food, which is called foraging, protein searching for binding site on a DNA, visual search when you're trying to locate a face in a crowd. So there are many different search mechanisms, and so there is not one single mechanism for a search phenomenon, but there is one robust class of models which are actually go by the name of the intermittent target search strategies. So this has a sort of combination of, essentially there are two time scales. So there is a phases of slow motion where you're actually trying to detect the target, and fast motion where you relocate but you don't really search. So just to give you an example, imagine that in the morning, so at your home you lost your car key. So you're searching for it. So you start with the bedroom, you search there, you don't find it. So then you relocate from the bedroom to the kitchen, and then you search there and you don't find it. So this is the relocation phase. And so there's a local search followed by relocation. Okay, so this is a general class of search phenomenon which actually applies to many of these situations like this. Protein searching for binding site in DNA is exactly like that. So there is one particular special case of this intermittent target search strategies, which applies to this visual search problem, so which I'm going to tell you about. So the visual search means basically that you're trying to locate a face in a crowd, right? So you go to a very crowded place and you're trying to find, your friend's face. So what do you do? I mean, nobody does, starts from one end and scans all the faces. So what people typically do is that you start from some initial condition here where you start your search, and you sort of, your eye does the diffusion locally, trying to find it. And if you don't find it, you come back to this initial point, and then you immediately, then you restart the process. And this is the sort of restarting or resetting. So you reset to the initial point, and then you again search locally here. And this is how the visual search works. Yeah, this is why I'll come to that. I mean, I'll show that this is indeed the optimal way to do this. Okay. So in fact, I mean, the psychologists, they do these experiments, so they take a patient and they put a camera in the eye, and they show a picture of a lot of bees, and there's one single bee in this picture, and they ask to locate this bee, okay? And this is what they typically see. They see that this, patient, starts from here, does kind of local search, always comes back to the initial point, and then again does search and comes back to the initial point, and so on. So if you look at the trajectories, they do precisely that. So they do diffusion, and then come back to the initial condition. Then again you do diffusion and come back to the initial condition, and so on. Okay. So this is the typical search pattern, and then goal is to finally locate the bee. And in case you haven't figured out where the bee is, it's here. So this is the only bee. So anyway, so this is the sort of this is people actually regularly do it, and and this is the sort of, in visual search, this is what happens basically. So you have a diffusion, and then with certain random rate, I mean with some exponentially distributed time scale, you actually come back to the initial point, and then you restart the process. Yeah. No, there is finite size effect, of course, and things like that. But I mean, imagine that this is a very big system. Okay. Yeah. Yeah. So now this resetting business actually has been around for a while, and in fact it was studied, to my knowledge, first time by Mandrubia and Zanet in multiplicative processes, then in network search, and in randomized search algorithms in combinatorial optimization problem. This is also routinely used. For example, I mean, just if you are doing simulated annealing algorithm to find the, the global ground state of some configurations in glassy systems, for example. So if you run your, just a simulated annealing algorithm, you might get stuck in a metastable state for a long time, right? So, you are trying to search for the global minimum, which is here, but you might get stuck here. And so you can keep on, doing search. It will take a long, long time. So what people empirically found is that instead of, keep on doing searching, if you again come back to the initial starting point and restart the search, that, empirically it was always more efficient. But there was no quantitative studies of how efficient it is, this search process. Okay? So this was our main motivation to, at least within a simple model, to get this, quantitative estimate of is it really efficient. Okay? So this was actually a few years back with Martin Evans. So we actually, wrote this very, very simple model of just a single particle diffusion in stochastic resetting, which of course you can generalize in many, many different ways. And so this is what I'm going to tell you about. And then if I have some time, I'll talk about the various generalizations of this process. Okay? So let me first start with this simple model, extremely simple model. And before coming to the search, I'll come to the search problem later. But let's just start a very simple model. Okay? So the model, and I'll want to talk about its steady state. So what is the model? So I'm defining in a one dimension, but you can easily generalize to higher dimensions. So basically what you have, so this is time and this is space. So you have just a single particle which starts at x0 at the initial point. And then it just does normal diffusion, one-dimensional diffusion, for example, here. And then with rate r, so r is not the distance, it's a rate. Okay, so this is a resetting rate r. So with rate r, you reset to the initial position, and then again it starts diffusing and so on. So mathematically, what you will write down the dynamics is a continuous time dynamics, continuous space, continuous time. So in a small time interval delta t, with probability r delta t, you go to x naught, starting point. So this is the position at time t plus delta t. So either you go back to the initial point with probability r delta t, and with probability 1 minus r delta t, you just diffuse. That means you just add a noise term, just a random diffusion, and this is just a Gaussian white noise with 0 mean and diffusion constant d. So that's the model, very, very simple. Okay? So for the moment, there is no target, just this model. So you ask, okay, what happens? So what is the probability distribution of the particle after some time t, or a long time? So the point is that when r is 0, there is no resetting, it's just a normal diffusion, and you just add this extra resetting event. So you just interrupt your evolution at an exponentially distributed time with parameter r, and you ask what happens to the final state of the system. Okay? So you want to look for what is the probability distribution xt, given that the resetting rate is r. Okay? And initial condition is just a delta function. You are at the x naught, x equal to x naught. Okay? So when there is no resetting, so we know that it's just a simple diffusion. So it's a Gaussian distribution with a variance which is t and dt and 2 dt, and then there's no steady state here, of course. Okay? Forever it spreads. Now you introduce this, switch on this resetting, r bigger than 0, and you ask, okay, so I had the Langevin equation, I'm going to write down the Fokker-Planck equation for that. How do I do that? I mean, you just, again, with probability 1 minus r delta t, you diffuse. That means if you want to be at x at time t plus delta t, you must have been at x minus eta t delta t at time t, and you have to average over this noise. And then with probability r delta t, you actually, you are at, when you are at x equal to x naught, with probability r delta t, you just reset, basically. So then from this, usual way, you expand this in noise and take the long time limit, delta t going to 0 limit, and you arrive at a Fokker-Planck equation, which is very, very simple. So you have the diffusion part here, and there is this term here. So this is a master equation. So this is actually a loss term. So if you are at x with rate r, you are going away from x. So therefore, you have this. And if you are at x equal to x naught, then from all other points, by resetting, you are coming here. So therefore, with a rate r. So this is the gain term, essentially. Okay? So this is the equation. Okay? So of course, when r equal to 0, you see that you are just normal diffusion. And then you ask, okay, so what is the what does these two additional terms do? I mean, what is the sort of steady state of this model? Is there any steady state? So this is the Fokker-Planck equation. So to get the steady state, you just have to put del P del T equal to 0, and you have to solve this ordinary differential equation, which is simple enough. And so you can obtain an exact solution, which is just an exponential minus mod x minus x naught. Okay? So you have a stationary solution, which is highly non-Gaussian, of course, and this alpha naught is just square root of r over d. So r is the resetting rate here. Okay? So first thing, comment is that this is, of course, it looks like a Gibbs state. It's like as if it's an effective potential, which is this linear potential mod x minus x naught. But actually, it's not an equilibrium because the steady state, there is it's a manifestly wireless detail balance because there is always, you are going to x naught by this resetting process. So therefore, it's actually in the configuration space, it's actually a current carrying state. I mean, there is always a current going from any point x to x naught. So there is a non-zero current in the configuration space, and so it's a non-equilibrium stationary state or non-equilibrium steady state, if you like. Okay? And so this is probably one of the simplest examples of non-equilibrium. You can explain to any undergraduate student also. This is really, really extremely simple, and you have a non-trivial non-equilibrium state here. Okay? And just by the simple resetting mechanism. Then you can actually generalize to higher dimensions. I mean, all that happens is that this diffusion term just becomes a Laplacian here, d-dimensional Laplacian. And again, you can solve for the stationary state. So instead of exponential, now is in general some Bessel function with an exponent which is 1 minus with an index which is 1 minus d over 2. And of course, for d equal to 1, it reduces to the exponential case. Okay, so there's a non-trivial stationary state in any dimension. Okay, so this is the first sort of observation. And so once you know this, then you can ask, okay, how does it actually relax to the stationary state? That is the dynamics. I mean, of course, it will finally approach the stationary state, but how does it do? And it turns out that even again in this very simple model, there is a very unusual temporal relaxation. And let me just explain to you how that works. So how do I solve this time-dependent solution? There are two alternative ways. Either you just solve this Fokker-Planck equation, which is simple enough equation, you can solve it. But there's a sort of better way of doing it, which is actually much more general, which is exploiting a sort of renewal structure of the problem, which is physically more intuitive. And let me just show you how that works. Okay. So how do I solve this? So I look at any particular history of this process. Okay. So there's a trajectory here. So again, this is resetting with R. I want the probability after this is time and this is space. I want what's the probability that the particle is at x at time t, right? So I look at my trajectory, and I look at the time at which, in that particular trajectory history, what is the time at which the last resetting happened? So suppose that time is tau backwards. Okay? So this tau, of course, is a random variable because it varies from one realization, one trajectory, one history to another history. So you ask, what is the probability distribution of this tau, the time since the last reset, given the final time t? And it's very easy because it's just a Poisson process, because with probability r delta t you are resetting, with probability 1 minus r delta t you are not resetting. So therefore, this is just an exponential distribution as long as tau is less than t. And if tau equal to t, that means there's no resetting. The probability of no resetting is just e to the power minus rt. Okay? So therefore, you can check that this is a normalized distribution given t. And so I know this distribution of this last time since the last reset. And once I know that, then it's very easy to write down the full solution at time t, because, okay, so let's say tau is the time at which the last resetting happened. Now, once the last resetting happened, it's a totally Markov process. So essentially, after that, it's a free evolution, right? So during this time tau, it will just evolve without resetting. So 0 means without resetting. And the probability for this resetting time itself is just this exponential distribution from here. And then you have to integrate this tau from 0 to t. And there is one possibility that there is no resetting, in which case just a free evolution all the way up to t from 0 to t. And this happens with probability 1 e to the power minus rt. And then you can check that indeed this solution satisfies your Fokker-Planck, this time-dependent Fokker-Planck equation. It's an exact solution of this equation. But you can derive it in a probabilistic way, which you can generalize later for other things. And when r equal to 0, you get back just the diffusion propagator, and because this term is not there, and you just get ordinary diffusion propagator. And you can check that when t goes to infinity, so you just have to replace this guy by 0 to infinity, and this term drops out, and this is what gives you the steady-state stationary distribution. So this is a full solution of your time-dependent Fokker-Planck equation. And so let's analyze it for large T. How does it relax? Okay. Now, typically, I mean, most systems that that it relaxes. There's a relaxation mode with exponentially. It relaxes to the steady state. Here also it does, but in a strange way. And the way it does, if we just analyze this into this full solution, so what you find. So I'm plotting here the space-time. Okay, so this is time. This is space. So if you look at a particular time slice, just fix a time t, and look at it as a function of x, and look at what is your, the density function as a function of x. So what you find is that there is a length scale psi of t, which is set by the resetting, and it increases, ballistically with time t. So as long as you are within this light cone, then the solution is completely time independent. But outside this light cone, in the green regime, so there it still depends on time t. So what is happening here is that there is a time-dependent length scale, which is, sort of moving like a front. And within the front, you have the stationary state established, but outside the front, it still remembers the initial condition. So this is, so this stationary state, this non-equilibrium steady state gets established on a larger and larger length scale as time progresses, because this length increases linearly with t. Okay? So this is a very sort of unusual temporal relaxation, even in this simple context. And so there is some kind of dynamical phase transition here, and you can quantify this by, No, it's just a normalization. Because you have the full solution. I mean, there's no, you can, just analyze. In fact, I mean, the way to analyze it, you can't do this integral exactly, but you have to just do by saddle point calculation. And then as long as there's a saddle point, you have the stationary solution. But when you don't have the saddle point, it sticks to the end, and you have a time-dependent solution. Okay? So you can actually write down this solution at late time t as in this sort of large deviation form. So it's exponential minus t into a rate function of this length scale x minus x naught over t. And this function I of y, this, it's just a alpha naught is square root of d over r times mod y. So it's, and then for y less than y star and y bigger than y star, it actually has a different form. So basically what you see is that this large deviation function, it is sort of non-analytic. It's first, it's continuous. Its first derivative is continuous, but the second derivative is discontinuous at this point here. Okay? So this is a second-order dynamical phase transition that happens even in this, extremely simple model. Okay? And this is actually quite generic, it turns out, not just for this model. Any model with resetting, this always happens. So now let me just go back to the original question I posed, that is the target search. So now my question is, does resetting really help, does it make the search process efficient or not? Okay, so that's the question. So let's try to analyze that. Again, very simple. So again, I'm just doing for the 1D, and then we'll generalize to higher D. So imagine that now you have a target, which is sitting at the origin here, fixed target. Okay? And you have your searcher, who is starting at x naught, and is just diffusing and to find the target. So first, let us consider just without the resetting, just what happens with a normal diffusion. Okay? So how do I sort of quantify the time? So this is just the first passage time. First time it actually arrives at the origin, it finds the target. So the time to find the target is just the first passage time. So how do you solve that? So what you do is you just define the survival probability. So Q0, this 0 means, subscript 0 means reset without resetting. So I start at x naught, I ask what is the probability that starting at x naught, the target survives up to time t. That means up to time t, the particle still hasn't found the target. Okay? And then, this is very easy to show that you can write down a backward Fokker-Planck equation. Backward, because you are, varying the initial position here. You don't care about the final position, just varying the initial position. So this is just a backward Fokker-Planck equation valid in the semi-infinite space, x not bigger than equal to 0. And you have to put the absorbing boundary condition, that is, if you start x not equal to 0, then this q should be equal to 0. Okay? So this is trivial to solve this equation. And you find that the solution is just this is a well-known result, it's the error function. Okay, so this is just the integral of Gaussian. And this is the survival probability. So therefore, the first passage probability, which is just the time derivative, so this is the probability with which it survives. Therefore, minus del t is the probability density of the time at which it finds the target for the first time. So just taking the derivative, you find that this is a well-known result. And you see that for a fixed x naught, as time goes to infinity, this decays as t to the power minus 3 by 2. This is the famous first passage exponent for the 1D Brownian motion, I think first derived by Chandrasekhar. And so this t to the power minus 3 by 2, the consequence of that is that the first moment is a power law decay. So therefore, the first moment of this is already infinite. That means the mean time to find the target is infinite if you have just simple diffusion. Okay? So you cannot find, I mean, basically, essentially, it's a very bad search process, just plain diffusion. You will have, because there are trajectories which will take you to plus infinity, and that's the reason you find it very difficult to find the target. Okay? So this is without resetting. So now we switch on the resetting, and you ask what happens. So how do I solve this problem? So again, I mean, I do the same trick that I used before. That is, for every given surviving trajectory, I look at the time since the resetting tau, and again, this has this distribution. It's a random time, basically. And given this time, so now I'm going to write down sort of the equation for this survival probability in presence of resetting. Okay, so let's see again. There will be two terms. So first thing is that given this tau, which happens with this probability, so you see that from here to here you have a free evolution. So that means this will be just q0 x0 tau. This is the probability that it survives starting at x0 up to time tau, right, without any resetting. And then you have to ensure that up till that time, t minus tau, it actually did survive with resetting rate r, in presence of resetting rate r. And there's a probability that there's no resetting, in which case you have just an additional term. So this is like a Swinger-Dyson equation. And so because you have to solve it self-consistently. But the thing is that you realize that there is a sort of convolution structure here. So a natural thing to do is to take the Laplace transform with respect to time t. And if you do that, I'm not, it's easy to show that the survival probability in the Laplace space in presence of resetting, you can write in terms of the survival probability without resetting, but the Laplace variable just gets shifted by r. Okay? So this is an exact answer for the Laplace transform of the survival probability in presence of resetting. Okay? And we know this answer already because without resetting, because the solution was error function in the real space, you just have to take the Laplace transform of that. And if you take the Laplace transform of this error function when r equal to 0, it's very simple. It's just this. So therefore, the final answer, the full answer is, this is the Laplace transform of the survival probability, and it's just given by this expression. Okay? And so now let's see the consequence of this. So I want to calculate the mean capture time, so which is again the first passage time, which is the time derivative of that, and the first moment of that. So mean capture time is just this Laplace variable evaluated at s equal to 0. And you find that this is a finite expression. Remember that r equal to 0, it was diverging. But the moment you introduce the resetting, it becomes finite. And it's given by the exact expression, which is this expression. And so you want to plot this as a function of r for a given initial x0 and the diffusion constant d. Because r is a parameter, your resetting parameter. And let's see what it does. So if you plot this function, okay, so first thing is that it's finite. When r equal to 0, it's infinite, but for any finite r, it's finite. Okay? No. We'll see in a minute. So, okay, so this is, so if you look at as a function of r, what you see is that this is a non-monotonic function. It's non-monotonic, that's easy to guess, because what happens, let's look at the case r goes to 0. So when r goes to 0, it's just, again, we have seen that already it's infinite. Now when r goes to infinity, so this is the r going to 0. So r going to 0 means that there are trajectories, I mean, which take you to basically go back to the plus infinity, so the average time to find the target is infinity. On the other hand, when the resetting is extremely large, That means what happens is that you are diffusing, but R is so large that you are always sort of getting back to the initial position. So it's almost the trajectory is extremely localized on the x0, and as a result, again, you will not find the target. Okay, so our the mean time again will diverge. So the two ends, it diverges here and it diverges there, and this is the exact functional form. But what you see is that this non-monotonic, so there is an optimal value of R star at which the mean capture time is minimum, and you can compute just by taking the derivative of this. So this optimal resetting rate is, okay, this is just a dimensionless number here, d over x0 squared, so that's the right dimension. And this gamma is just a solution of this transcendental equation. It's just found by taking derivative of this equation. So you find that gamma has a non-trivial value, which is 1.59. So there is an optimal value of the resetting rate at which the time to find the target is minimized. Okay, so indeed, the process with resetting is more efficient, and moreover, there is an optimal value of the resetting rate, which makes it the most efficient, if you like. Okay? So coming back to question of Frederick, so what happens in higher dimensions? So higher dimensions, if you want to solve this problem, then you have to give a finite size to the target, because for d bigger than 2, if you're a point target, you can never find it by continuous time Brownian motion. So therefore, you have to give a cutoff, basically. So you just assume that your target is a small sphere of radius a, and you again start your searcher at some point r0, capital R0, and again it diffuses and it resets with rate r. Okay? And so again, you can, I'm not going to show you the solution, but same method works. Essentially, you have to solve in d-dimensional Fokker-Planck equation, and again this Swinger-Dyson equation, and so the final answer is that mean first passage time is again given by this expression, and this is just the Bessel function within mu equal to 1 minus d over 2. And if you plot this again as a function of r in any dimension, there is an optimal value of r star that minimizes this mean search time. Okay, so this is the sort of, since I'm running out of time, I'll just. So this is the sort of basic, if you like, the Green's function. So once you have solved this problem, then you can actually generalize in many, many different ways. So for example, you can ask, okay, what happens if the resetting rate is not a constant r, but it actually depends on the position x, where the particle is there, and what is the optimization strategy? And then you can also ask that maybe the target is not at a fixed position, but it's some, you don't know exactly where the target is, but there is a distribution of the target position, and so where should the particle reset? And similarly, you can, here I'm resetting only to the initial point, but you can say that I can reset to any arbitrary point, and so you can work it out, all these things, once you know the basic solution. And so as I said, it's like a Green's function. If you want to solve a problem with some source term, so you just solve the Green's function and then integrate over the source term with that. So you can actually, ask many other different questions. And finally, this one thing we worked out with Martin and Kiran Malik is, so you can actually, what you see is one dimension, for example, that the final stationary state is, up to some proportionally constant, is exponential minus this effective of x, which is just this alpha naught mod x minus x naught. So it's as if it was like, diffusing in a potential, which is just a linear potential. So you can ask, okay, what happens if I look at the equilibrium dynamics in this potential? So I just write down the Langevin equation in this plus some noise. And I can, write down the Fokker-Planck equation and solve the first passage problem and find out what is the, mean time to come back to the origin. And so this is the equilibrium dynamics, whereas the resetting is really non-equilibrium dynamics. And you can ask which one is better. And it turns out that not for this model, for a wide class, for all models that we came across, it's always true that the optimal, the optimal mean time to capture the particle is always better in this non-equilibrium setting than the equilibrium setting. Okay? So let me just summarize and conclude. So essentially, the main point is that just the diffusion with stochastic resetting reaches a sort of new sort of non-equilibrium stationary state in all dimensions. And And the point is that this is not just with diffusion. I mean, you can take any dynamics, whatever your favorite dynamics is. You have your model, it's evolving under stochastic or deterministic dynamics, and you just interrupt it at random times, exponentially distributed, let's say. And you keep on doing this. I mean, it's like, for example, a population is growing and there's a catastrophe, and it sort of goes down to 0, and again it grows, and again it goes down to 0. And if you wait for a long enough time, then you will always reach a non-equilibrium stationary state, which is highly non-trivial. I mean, I just showed you just one example of a single particle setting, but this is much more general. And it's always this, also accompanied by this unusual temporal election, and there is a second-order dynamical phase transition. And indeed, for the search context, the resetting does make things efficient. Okay? So this was, as I said, in the combinatorial optimization literature, this was known empirically. People always found that if they reset, they somehow, they find the ground state much faster. And but there's no quantitative estimate. But at least in this context, simple context, we have a, we can prove that this is true. And then, of course, you can generalize in other ways. So, for example, instead of diffusion, if you just take a Levy flight, and again, the same phenomenon occurs. That is, there is an, resetting always makes it sort of more efficient in the search process. And then, last 2 years, I mean, resetting has been studied in, various other single particle context. For example, in the context of enzymatic reactions in biology. Then it has been generalized to many searchers, and then with memory, non-Markovian models. And but I don't have time to go through all this. And also in a many particle, spatially extended system. So, for example, if you take a fluctuating interface, like which is evolving via, let's say, the Karda-Parisi-Zhang equation or Edwards-Wilkinson's equation. So, an interface h of xt, and it has the equation of motion, which is this natural dynamics, basically. So, let's say in 1+1 dimension. So this is the natural dynamics of this. Is the extended system, and you evolve it, and then you just stop the process, and you restart from the same initial condition. Okay, and you ask what happens, and what happens is that indeed now if you look at the probability of the height at a particular point in space as a function of time t, long time limit, it actually approaches again a non-trivial height distribution function. And this was work done with my ex-postdoc Shamik Gupta and Gregory Sher. And also it has been studied in other contexts as well. So, so the main point that I wanted to make here is that just this simple resetting, it actually sort of takes the system to a sort of non-trivial, non-equilibrium steady state, and you can actually solve many things analytically, which is very nice. And but this is actually very general. I mean, it's like no matter what system you are looking at. For example, you can just take just a Ising model evolving under global dynamics, and you just evolve it in zero temperature dynamics, let's say, and evolve up to some random time, and then restart again from the initial condition. And the system actually again will go to a non-equilibrium steady state, which is highly non-trivial. Okay? So there is a lot of interesting things, and I think a lot of work which is being done right now over the last couple of years. And let me just acknowledge my collaborators who started this work with Martin Evans, and then various other people, and Gregory also at Orsay, been working quite a lot, and there are some references here. Thank you for your attention.